Okay, so we're just gonna pick right back up where we left off. So we said one possible strategy for J is DDD. So what that just means is in the first period, J defects. In the second period, J will defect if K played C. And in the third period, J will defect if K defected. So what that means, of course, is just that J is going to defect no matter what. Okay, so here is a quick little claim. So we can claim in Prisoner's Dilemma played twice. So by the way, we're going to call that sometimes Prisoner's Dilemma times 2. So in Prisoner's Dilemma played twice, well, it's going to be a Nash equilibrium if the first player plays DDD and the second player plays DDD. And so the explanation for this is going to be more, well, here's the explanation. Suppose, for example, that K plays DDD. Well, if J plays DDD, then J gets a payoff of 0 plus 0 is equal to 0. And there's no way for J to get higher than 0. Right? There's no way that if, no matter what J does, it's not possible for J to get a score that is higher than 0 just because K is always playing defect. So this is the best J can do. So DDD is a best response. To DDD. And so, of course, that means that we have a Nash equilibrium. So that's not the only Nash equilibrium, right? So there are some other strategies that J. Actually, I take that back. Let's hold off on whether that's the only Nash equilibrium if we repeat the Prisoner's Dilemma twice. Okay, so let's talk about the next step then, and so that's going to be to talk about a larger Prisoner's Dilemma repeated game. So let's jump all the way to Prisoner's Dilemma repeated 5 times. And so, of course, a player's payoff is going to be the sum of their payoffs in each of the 5 Prisoner's Dilemma games. Just very analogous to how we did it with playing twice. Okay, so if we play Prisoner's Dilemma 5 times, well, first of all, I should just point out that a strategy now is very long. So a strategy will say, what should J do in period 1, and then what should J do in period 2, depending on each of the 2 things that K has done. Maybe I should write this down. It's probably getting a little bit complicated to listen to. So an example, or let's say it this way. So a strategy for J is, so this is J in period 1. J in 2 if K did C in period 1. J in 2 if K did D in period 1. And then, so J has to now do something. So there's going to be J in 3 if K did CC in 1 and 2. And so a strategy in general could be extremely long, right? So J's 5th period action may depend on every single different combination that K could do in the first 4 periods. So this is going to get really unwieldy if we try to go through one by one, right? We don't want to do that. So we want to think of something a little bit more clever. And so here is our idea here. So we can say, so I claim that the only Nash equilibrium outcome in Prisoner's Dilemma played 5 times is DD, DD. So in all 5 periods, they'll play DD. So, by the way, this idea of the Nash equilibrium outcome, so what we're saying here is, what will they actually do? What will they actually play in a Nash equilibrium? So here we are not specifying all of the different strategies off path. And so what we're saying is, if you have a Nash, they must be playing DD in every single period. So we're not necessarily saying, for example, that that the players are just playing D no matter what. We're just saying that in the actual strategies that they play D. Okay, so let's talk about how we are going to verify that that is the case. So here's the idea. So in the 5th round, in a Nash equilibrium, they must play DD, right? Like if you think about some game, some combination of strategies where I told you, hey, this is Nash, and in the last round the players play CC, you would say, oh, that's not Nash. That can't be Nash because either player could have gotten a higher payoff just by doing the exact same thing they were doing and then playing D in the last period. So our conclusion is, in the 5th round, they must be playing DD in a Nash equilibrium. So this is going to sort of unravel, and maybe you can sort of see where we're going. But what we can say is that in the 4th round, in a Nash equilibrium, well, again, they have to play DD. Right, and the reason that we know that is because, well, if we're talking about a Nash equilibrium and we know that in the 5th round they're going to play DD, well, then in the 4th round they also have to play DD. One way that you can think about the logic here is a 5-round version of Prisoner's Dilemma. That's basically the same thing as saying we're going to do a 4-round of Prisoner's Dilemma and then play Prisoner's Dilemma. And, well, if you know that in the last one they have to play D and D, then they must also have to play D and D in the 4th round. So in the fourth round, they have to play D and D because they'll play DD in the fifth round. So of course we can just sort of keep this going. So in third round, in Nash Equilibrium, they play DD, and so on. So of course, second has to be DD by the exact same logic. And in the first round, they have to play DD. And so that is why we can say that in a Nash Equilibrium, the only outcome is Prisoner's Dilemma 5 times. Excuse me, the only Nash Equilibrium in the Prisoner's Dilemma 5 times is DD all 5 times. All right, I'll take a break here, and I'll be right back in just a moment.